Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to our MOOCs course on the topic of fundamentals of nuclear power generation, and today we are going to start the 5th module on reactor thermal hydraulics. The term thermal hydraulics, some of you may be aware about it, some of you may not be. So, just to update on this, the term thermal hydraulics involves the term thermal and hydraulics. So, can you guess from there what it may refer to? Of course, thermal is associated with the analysis of heat transfer, and hydraulics is associated with the analysis of fluid flow, and therefore, the term thermal hydraulics is generally used for simultaneous analysis of heat transfer and fluid flow problems. And hence, in this particular module, we are going to look at the heat transfer aspect and also the flow aspects whenever necessary of a nuclear reactor. To start with, just a quick look back at the 4 modules that we had. Like I am taking you back to the first module itself, where this picture was shown. Whenever a neutron or strikes a uranium-235 nucleus, it initially forms a temporary nucleus in the form of uranium-236, and then we have the fission reaction when this intermediate nucleus or isotope breaks into 2 much lighter isotopes. In this case, it is krypton-92 and barium-141 plus 3 neutrons, and it is also associated with a large amount of energy. In the first module itself, we have learned whenever such a reaction is given, without trying to understand the inherent physics of that, we have learned that how to calculate this amount of energy release. We know that whenever we know the values of this mass, we can calculate the mass defect, that is the mass of combined mass of the products will be generally slightly higher than the combined mass of all these reactants, and this difference was termed as the mass defect, and we know the mass defect multiplied by c square can be related to the total amount of energy that has been released during this reaction. Whenever we are having any reaction, even in common chemical reactions, there is generally small amount of mass defect, but the amount of mass defect that generally we get in a chemical reaction is negligibly small compared to what we get in case of a chemical reaction, and therefore, chemical reactions are than we get in a nuclear reaction, I should say, and that is why in nuclear reaction we get huge amount of energy release, which can be of the order of 10 to the power 6 to 10 to the power 7 times greater compared to a equivalent chemical reaction. So, in the first module itself, we have learned how to calculate this amount of energy once we know the mass of all these components involved. But in the second module, we learned that while there are several nucleus which can undergo spontaneous radioactive decay, this particular kind of fission reaction is generally not common, or it does not happen naturally. Rather, we have to induce this kind of reaction by striking the nucleus with a suitably charged particle, which comes under the category of artificial radioactivity. And even when we strike a nucleus with a particle, commonly neutron is the most suitable particle, we can have different kinds of reactions, like we can have scattering, which is associated with both elastic and inelastic collisions, that is neutron and nucleus may exchange their momentum and energy, and can have a perfect conservation of both kinetic energy and momentum in case of an elastic collision. In case of inelastic collision, we have some amount of energy release as well. We can also have some kind of transfer reactions. Only in very small fraction of total situations we can have the neutron being absorbed in the nucleus, and whenever the neutron gets absorbed in the nucleus, it is not guaranteed to have fission reaction. Rather, we have learned in the third module that there is only a fraction of this total neutron that gets absorbed can induce fission. Like when an uranium-235 absorbs a neutron, only in 85% case we can have the fission reaction, in remaining situation we may have the non-fission capture to produce uranium-236 isotopes. And whether this reaction at all will happen or not, that strongly depends upon the energy of the neutron and also on the nucleus itself. Like the equation that I am showing here, this particular reaction, that is valid only for thermal neutron, that is a neutron which are having energy of the level of 0.025 electron volt. A higher energy neutron generally will not cause such kind of reaction for uranium-235. So, in the fourth module we give a much closer look to the neutrons, particularly the distribution of neutrons inside the reactors. We have seen the power produced during reaction can be given by such a reaction like this, where this particular term is associated with the amount of energy released during fission. Here ER, this one is the amount of energy released during a single fission reaction, which is generally of the order of 200 MeV. Sigma F is a macroscopic cross section, and this is the neutron flask, generally the thermal neutron flask. But here as a neutron can have neutron can pass through different energy level in reactor. So, we need to integrate this over all possible energy levels at any particular location, and then to get the total energy produced by the reactor, we need to integrate this over the entire volume. So, now we more or less know about how to calculate the neutron flux distribution, like we have studied different cases in the previous module. And once we know the neutron flux distribution, the knowledge about ER and sigma F are more or less standard nowadays. And so, just by knowing the neutron flux distribution, we can more or less calculate the total power that has been produced by fission inside a reactor. But once we have the power, then what to do with that? Of course, we need to transmit the power to some coolant stream, which will be used for subsequent power production. And in this particular module, we are going to look at that particular power transmission or energy transmission procedure. Now, to start with, I probably have mentioned earlier that commonly we can classify nuclear reactors into two categories, homogeneous and heterogeneous. A homogeneous nuclear refers to the one where we have an uniform distribution of all the substance that may be present inside the reactor. That is, from the entire volume of the reactor, let us say this is one reactor. Now, if we pick up a sample from somewhere here, another sample from somewhere here, and a third sample from somewhere here, all these samples should have identical chemical composition, and then only we shall be calling it a homogeneous nuclear reactor. Generally, in a homogeneous reactor, we have a soluble nuclear salt, commonly sulfate or nitrate salts of uranium, which is dissolved in water. Now, that water can be the normal water or it can be heavy water also. Just remember that heavy water refers to the water where hydrogen is actually deuterium. So, here the nuclear salt is generally dissolved in normal or heavy water, and also acid can be sulfuric or nitric acids. And this kind of, because of the presence of such an aqueous solution of nuclear fuel, they are also called aqueous homogeneous reactor or AHR. They are also sometimes called water boilers. Do not get confused with boiling water reactor, which is a common type of nuclear reactor. Water boiler refers to these AHRs, because the water molecules that can be present inside the reactor, they can go through a kind of decomposition process when that is subjected to the radiation. Such kind of because of such kind of radiolytic decomposition, hydrogen and oxygen bubbles may appear inside this reactor, and that is why they are called water boilers. This is a classical picture of a very old and popular AHR developed in the Oak Ridge National Laboratory. We do not want to go to the details of this, just for your idea, where we have a common vessel, and inside the vessel, inside this pressure vessel, like this one, inside this pressure vessels, we have this aqueous solution of the nuclear fuel, and everything takes place inside that. You can see it is a 60-inch diameter, which is a very large one. Now, homogeneous nuclear reactor offers several advantages, like it can attain criticality with natural uranium itself. If you think about the earlier analysis of multiplication factor that we have done, to have a criticality condition, we need to have a large value of this thermal fission factor, and also significantly large value of the thermal utilization factor. Now, A natural uranium has only 0.7% of uranium-235, rest is uranium-238. Therefore, it can have quite significant value of this resonance absorption probability, but still because of the large volume and uniform mix, large volume of the shell and uniform mixing of fuel and moderator, the homogeneous nuclear reactor generally can attain criticality with natural uranium itself. And quite frequently they are also used with enriched uranium, and if they are used in enriched uranium, they provide an excellent specific fuel requirement, which is generally very low compared to other kind of reactors, that is heterogeneous nuclear reactors. Neutron economy is also superior in case of homogeneous version, because the neutrons are surrounded by neutrons and fuels on all the sides, and therefore, that is every neutron is surrounded either by moderator nuclei or fuel nuclei, and therefore, there is excellent neutron economy compared to heterogeneous version. They are also very good in self controlling and can handle large increase in radioactivity because of their large volume of moderator and coolant present inside this. However, homogeneous nuclear reactors are not very popular for commercial use because of their challenging kinetics and control issues. While they have very good self controlling feature, the external control is quite difficult, again because of that homogeneous mixing only. We can't independently control the reactivity, yes, because once we get the reactor started, we do not have exclusive control on the mass of fuel and the mass of moderator that is present there, and also we do not have a direct control on the reactivity. So, AHR is primarily limited to research reactors, lab scale small reactors till date. A big problem for them is also the use of the sulphate or sulfuric acid. Uranium sulphate in water leads to the production of sulfuric acid, and such hot sulfuric acid is extremely corrosive to stainless steel, which is one of the common materials used in nuclear reactors. And also the appearance of hydrogen and oxygen bubbles because of the radiolytic decomposition is another big issue from control point of view. When we are using the uranium nitrate as the fuel, then we do not have sulfuric acid, rather we have hot nitric acid. Nitric acid is much friendlier to stainless steel, that is, it does not corrode stainless steel that much, but everyone knows how difficult it can be to handle nitric acid, particularly at higher temperature. So, these are the reasons of not using homogeneous nuclear reactors that much for commercial power generation, rather they are more restricted to much small scale use, like the medical isotope separation from inline fuel, or also using that radiolytic decomposition, the production of hydrogen. And while homogeneous nuclear reactors are till date mostly restricted to experimental or lab scale reactors, heterogeneous nuclear reactor prevails almost in all possible applications for new commercial power generation. In heterogeneous nuclear reactor, we have material, the fissionable material, that is a fuel and moderator kept separately, but they are generally arranged in some kind of regular pattern, some kind of repeatable regular pattern, and every fuel component is generally separated by moderator with the adjacent fuel components. Just represent a picture like this. Here the red blocks are actually fuel, which are surrounded by moderator, this yellow colored one, from all possible sides. The coolant is flowing, this blue line refers to coolant through which is flowing through the reactor core, and therefore, all the energy that has been generated because of the fission reaction that are taken by this coolant stream. We can also have the control rods, which are one of the controlling elements. We will be discussing them in the next module. This is just a representative picture, but this red blocks of fuels that we can find in practical cases also they look more or less the same. We generally can have two types of designs. One, we can have plate type of reactors, that is not reactors, I should say plate types of fuel elements, where every fuel element is shaped like a rectangular plate, very thin rectangular plate I should say, and then immersed into moderator. Other possible design can be of circular cross section, cylindrical design. Again, the diameter of the cylinder generally is kept quite small compared to its height. There are generally longitudinal elements with polygonal cross sections which are arranged adjacent to each other. Hexagonal cross section is the most common one. just like shown here. Here all the circular elements are the fuel rods. Cylindrical fuel elements are called fuel rods. These circles are fuel rods, and all the gaps in between are occupied by moderator or the coolant. We can also have rectangular or triangular cross sections in nuclear reactors, but hexagonal is mostly preferred. Now, nuclear reactors can be classified into different categories as well. Actually, from now onwards we are not going to use the term heterogeneous, because we are going to talk only about heterogeneous nuclear reactors. And heterogeneous reactors can have several kinds of classification. Like one common classification is based upon the neutrons that are being used inside. So, based upon the neutron flux profile, we can have fast neutron reactors or fast reactors, and thermal neutron reactors or thermal reactors. Fast neutron reactors of course utilizes fast neutrons for their operation, and hence they must use a fuel which has some significant value of this fast fission cross section. Similarly, thermal neutron reactors utilize thermalized neutrons. So, there is a big role of moderator in case of thermal reactors. Based upon moderator, thermal reactors can be classified as the light water moderated reactor, heavy water moderated reactor, and graphite moderated reactor. Here I would like to mention again that light water generally is a quite bad term, because here we are talking not about any water which is lighter than the common fluid, rather we are talking about the common water itself. But still, just to differentiate them with heavy water, this term is universally used in the case of the nuclear field, and therefore, at least in this kind of names we have to use this light water reactor kind of terminologies. Now, there can be three kinds of moderators, like normal water, heavy water, and graphite. And this light water, so called light water reactors, again can have two principal classifications: boiling water reactor and pressurized water reactor. There can be quite a few others also, we shall be talking about them later on. Similarly, graphite moderator reactors also, depending upon the nature of the coolant, they can be gas cooled or water cooled. And in case of fast neutron reactors, what can be the moderator in a fast neutron reactor? What is the purpose of moderator? The purpose of moderator is just to slow down a fast neutrons to the thermal neutron level, and in a fast reactor we are looking to utilize the fast neutron itself, and we are not at all trying to slow it down, and therefore, a fast neutron reactor does not have any moderator, rather it the fast neutron itself induce fission to the fuel and transfer that energy to the coolant. Fast neutron reactors are generally liquid metal cooled, that is, they use liquid metals as the coolant in them. This is a common schematic diagram for a pressurized water reactor. In case of pressurized water reactor, the water is maintained in single phase by using a pressurizer. The pressurizer maintains a pressure inside the reactor such that maximum temperature of water is not allowed to cross the saturation temperature, and hence we are having single phase operation. And this is a boiling water reactor. In case of a boiling water reactor, the water or the fluid is allowed to boil and gets converted to steam, or I should say a part of that water gets converted to steam, and the steam is taken through the subsequent processing in the form of turbine and expansion in the turbine and condenser and pump, and again back to the core in the form of recirculation. So, we can have wide variety of coolant, as we can see from here. Both these two figures refers to light water reactors, but in one case we are using single phase water to carry all the heat produced by nuclear fission, whereas in the other case we are using the phase change process to carry the heat from the nuclear reactor. We can also have gas cooled reactors, which again quite similar to the pressurized water reactor. They remain in single phase gaseous medium, but the gas is allowed to circulate through the core and transfer the heat to subsequent downstream operation and then come back again. Same about liquid metal cooled reactor. They are also similar to PWRs, that is, the coolant is a liquid one like liquid sodium or liquid potassium, and that remains in that same state throughout its operation. There can be several types of nuclear fuels that we can find. One can be oxide fuels. It is quite common to find uranium oxide or plutonium oxide or a mixture of that as a fuel inside the reactor. Like oxide fuels generally offer very high melting point compared to the pure metal itself, and also as they are already in the oxide form, so there is no possibility of any further oxidation, thereby expanding the thermal limit of operation. Oxide fuel commonly can be just uranium oxide. Uranyl nitrate generally reacts with some basic substance like ammonia to produce U3O2, which is subsequently converted to uranium oxide by heating it in an environment of hydrogen or argon, generally a environment of inert gas. Other can be MOX. MOX actually refers to mixed oxide. Mixed oxide means here the fuel comprises of both uranium oxide and plutonium oxide. Plutonium oxide can comprise about 20 to 25% of the total mixture, and they are found to be behaving like low enriched uranium, like that is even in the mixture when we are using natural uranium, but the overall multiplication factor is found to be improved compared to what we get with pure uranium or natural uranium. Other kind of fuel can be the metal fuel, where using the pure metal itself or maybe some alloy of that. They are always characterized by much higher thermal conductivity and also very high density of the fissile nucleus compared to the oxides, but their temperature level or applicable temperature level is restricted. If we go to higher temperature, the metal may melt or it may get oxidized. There are several examples for this metal fuel. One can be the Triga fuel. Triga is a very popular type of nuclear reactor which has been used by several countries, and it is actually an alloy comprised of uranium, zirconium and hydrogen, and it has actually a negative temperature coefficient of reactivity, which is very interesting. Negative temperature coefficient of reactivity refers to as the temperature increases, reactivity starts to decrease, and therefore, there is no chance of reactor meltdown. That is, at higher temperature or when the reactor temperature keeps on increasing, the reactivity keeps on decreasing, and in a self sustained way the reactor is able to control its own temperature. There can be actinide fuels. Actinide actually refers to all these elements which can act as nuclear fuel. Uranium and plutonium are the two major actinides. Other fuels which are having its atomic number greater than 94, that is after plutonium, they are generally called minor actinides. So, actinide fuel generally refers to a typical alloy of zirconium, uranium, plutonium and several minor actinides. They are used in fast reactors. Third is the molten plutonium. Plutonium is also alloyed with some other metals to lower its critical point, and it is commonly used in research reactors, particularly when experimenting with fast breeder reactors. There can be ceramic fuels as well. Ceramic offers very high thermal conductivity and melting point, but they are prone to neutron induced swelling. That is, at higher temperature there may be a significant change in its volume. There we can have commonly uranium nitride and uranium carbide as the two ceramic fuels. And the final category is that of the liquid fuels. Liquid fuels are generally used in the homogeneous reactors and not that much in heterogeneous reactors for obvious reasons. Liquid fuels enhances the passive safety compared to solid fuels because of automatic load following capability like we have in case of homogeneous reactor. They can also retain the fuel mixture for significantly longer period, thereby affecting the fuel efficiency. So, with all these kinds of fuels in any reactor, while choosing the fuel we can consider several factors like the fuel must have a very high fission cross section. Secondly, it should have a very high thermal conductivity. If the thermal conductivity of the fuel is high, then the temperature change across the fuel itself will be quite small. These are common values of thermal conductivity. Like for metallic uranium, thermal conductivity may vary between 25 at 25 degree Celsius to 42 watt per meter Kelvin at 665 degree Celsius. For uranium oxide, it is much lower, just of 2.5 watt per meter Kelvin. Whereas for plutonium also has a conductivity lower than uranium, which is something like 4.2 watt per meter Kelvin. At higher temperature, the fuel should have sufficient mechanical strength so that it can maintain its own shape and doesn't get deformed. Like uranium is unusable beyond 665 degree Celsius because uranium can have several crystalline phases like alpha, beta and gamma phases, and beyond 665 degree Celsius there is a translation from alpha phase to the beta phase. Uranium can also react with oxygen at high temperatures and get oxidized. And another problem with plutonium as pure fuel is it also has several crystalline phases, and therefore not suggested to be used at high temperatures or at least high core temperatures. The temperature range available for operation should also be large, and that is possible only when the solid fuel has a high melting point. Like for pure metallic uranium, the melting point is something like 1133 degrees Celsius, whereas for uranium oxide it is significantly higher, it is greater than 2800 degrees Celsius. That is one of the reason of not using metallic uranium, rather uranium oxide as the fuel in modern reactors. And finally, they should also have good corrosion resistance characteristics, because they generally remain in contact with flowing coolant, which can cause or at least can try to cause significant amount of corrosion. Then we come to fuel pellet and fuel cladding. Pellet refers to each small module of fuel element which can be of the shape of small bullets or maybe just like a small tablet, and they are covered by a jacket which is called cladding. Cladding serves several important purposes, like this is a much elaborated diagram where you can clearly see each of the fuel modules here, like this is the one, this one is a fuel module, and this module is being covered by the cladding material. So, several fuel modules, each one is put on top of the other one, and they are connected from energy point of view, and their cladding is also a common material, and hence the cladding must have can serve several important functions, like they can provide the structural support to the fuel and they will prevent distortion. That means at higher temperature, even if the fuel gets softened or becomes soft, then it can't go just directly into the coolant stream, rather they will remain inside this cladding tube only. Another advantage is to prevent leakage of radioactive waste to coolant. The radioactive waste that are being produced, that generally remains inside the reactor itself. Later on they can be, means once their lifetime finishes, they can be used as this spent fuel. And finally, this so radioactive leakage of this waste to the coolant can be avoided. And finally, when in case of gas cooled reactors, you know that compared to liquid, gas generally is associated with much lower heat transfer coefficient, and hence they need some kind of extended surfaces or fins for heat transfer. And this cladding, by properly designing the cladding tube, we can also enhance the heat transfer in case of a gas cooled reactor. So, what should be the desirable properties for the cladding? Quite similar to the nuclear fuel, that means they should have a low absorption cross section, and the thermal conductivity should be high. That means whatever energy the cladding receives from the fuel, that is able to transmit that immediately to the coolant. The first point I must go back, low absorption cross section we have to ensure, because if the cladding itself starts absorbing neutron, then that will be a type of loss. Then it should have good mechanical strength at high temperature, so that it can support the fuel itself. And finally, cladding material should have chemical compatibility with the fuel and the coolant, particularly the fuel. This fuel, cladding and coolant, all these three materials generally must have compatibility with each other, and so is the moderator. These are the common cladding materials, like aluminum can be used only for temperatures less than 300 degrees Celsius, and the second very important cladding material can be magnox, which is actually an alloy of magnesium, and it can have aluminum and barium along with magnesium in it, and it can sustain up to a higher temperature of 450 degrees Celsius. Third one, that is the most preferred one, zircaloy, which is an alloy of zirconium and contains small elements like tin, iron, chromium, nickel, etc. And finally, stainless steel can also be used, but stainless steel may have its own issues. So, once we know about the structure of the fuel, we are now ready to study the energy analysis or perform an energy analysis of a reactor or maybe just a single fuel element. We know that every fuel is covered by a jacket called cladding, and therefore, the energy that is produced inside the fuel, if we are particularly talking about a solid fuel, the energy produced inside the solid fuel that will get conducted through the solid from its center line to the wall, and from the wall of the fuel the cladding is there. So, that heat has to be conducted through the cladding material as well, and then only it will be able to come in contact with the coolant. Now, this is a brief schematic representation. If Q is the amount of energy that has been produced by the core, and if coolant is coming with some temperature and going out at some elevated temperature, then we can write a simple energy balance as Q dot equal to m dot into integral of dH, where Q dot is the power production rate and m dot is the mass flow rate of the coolant, and hence it is m dot into H out minus H in, assuming that m dot remains constant. This is of course under steady state, this energy balance has been written. If the coolant retains the single phase status throughout this passage, then we can always write this thing, because we know as per the definition of specific heat, dH equal to Cp dt, or Cp is equal to dou H dou T at constant pressure. And that is why we can for single phase situation we can write this way. If Cp remains constant, this is a very straightforward integration, but generally Cp is a strong function of time, particularly at higher temperature, that can show a quadratic kind of relationship. And if the coolant changes phase, then situation is slightly more complicated. Then this energy balance can have two components, where the first one, this is the single phase energy right from the inlet temperature to the saturation temperature, here HF is the saturated liquid enthalpy, and this is the latent heat transferred, where this X is the quality or the mass fraction of the supplied coolant, which has been converted to the vapor phase. Now, this expression we have found earlier, energy released by because of fission per unit volume can be given an expression like this, where E R is the amount of energy released because of fission, sigma f is the macroscopic cross section, phi is the flux distribution by the neutron. Now, let us take a look at this particular chart. We have earlier mentioned that because of fission reaction, there is about 200 MeV, slightly greater than 200 MeV actually, amount of energy is released, which corresponds to the mass defect. But how that energy is being transmitted? Of course, the fission fragments take care of the majority part of that, which is about 160 MeV. But there can be several other components like fission energy carried by the beta and gamma rays or by the neutrinos, the fission, and also there can be a significant amount of energy carried by the gamma rays, which are released during this reaction. But out of this all this possible contribution, actually this 168 MeV from the fission fragments and this first 8 MeV from the beta rays combined together are usable or available as thermal energy. Rest are available either energy through radiation or by some other means, something like delayed neutron decay, etc. And hence, while we had a total figure of 207 to deal with for this year, practical case we are going to get only about 80% of that, and hence this year must be substituted with an effective value of that, which generally is about 80% of this theoretical level. And hence we can perform this integration as an approximate summation, where we are considering say multiple groups of the neutron flask. So, E r prime being a constant is outside the integration, and here J refers to here J is the each of the small neutron groups that we may consider. Like if we remember from the previous module that in a reactor we can have several groups of neutrons, and therefore, we often adopt a multi-group approach, that is, we divide those neutrons into several groups and sum their and perform the calculation for each of them, and then sum that over the entire range of energy available, and the same has been shown here. Here G refers to any particular such group, Nj is the total number of nuclei present there, and sigma Fj is the average fission microscopic fission cross section under that group, and phi of course is the neutron flux distribution of that energy level. We already spent lots of time in the previous module discussing the distribution of this phi, and let us take one result from there. This is the one result that was shown there for a cylindrical reactor or a cylindrical fuel element. Here this J naught is the this particular J naught is the Bessel function. Okay. ER is the energy released during fission, that 200 MeV the order of, and this one, the sigma F bar, is the averaged fission cross section of the reactor. P is the power production or power rating of the reactor, and this V is the volume of the entire reactor. So, capital R refers to the radius of the cylinder and capital H refers to the height of the cylinder. Now, let us consider a heterogeneous reactor which has smaller number of cylindrical fuel rods. So, each rod can be viewed like a cylindrical reactor kind, and each of these rods are having a radius of small a and height of h. Then the average macroscopic cross section can be calculated like this, where pi square h is the volume of each fuel rod multiplied by n gives the total volume of all the fuel rods, and pi r square h is the volume of the reactor itself. So, we can simplify this as a form like this. Now, if we put this expression for sigma f in the above expression, then we get like this, which finally simplifies to a form like this. So, finally, putting this expression for phi in the previous slide's expression, we get the volumetric rate of energy generation of a form like this. Here, just note that ER and ER prime both appears, where this ER refers to the amount of energy released during a single fission reaction. This is a theoretical value, and ER prime is the effective value of that ER, which can be recovered in the form of thermal energy. But still we are using this ER in the denominator, because while calculating the power rating for a reactor, generally the ER is used. As ER prime, ER is more or less constant, but ER prime that may vary from one situation to another. So, like say this is our reactor, the cylindrical reactor, this is the central line. We are taking this as a coordinate system. So, center line refers to r equal to 0. In the vertical direction also, let us take the middle of the cylinder as the coordinate system. So, here z starts from here, and hence if we put r equal to 0 and z equal to 0 in this expression, that is if we are talking about this particular location, then it reduces to a form like this. Actually cos 0 is equal to 1 and z naught 0 is also equal to 1. It asymptotically approaches 1. So, we get this as the expression of the maximum volumetric rate of heat generation, and putting that, the final expression gets simplified to a form like this. So, this way, by knowing the nature of the medium and nature of the heterogeneous medium, and also using the standard solutions, we can always calculate the total amount of energy that is available to be transferred to the coolant. So, let us take or consider a couple of simple situations. Our first case is that of a plate type fuel element. As I have mentioned, commonly reactors have two kinds of fuel pellets, one is of a plate kind, other is cylindrical or fuel rod. So, here we have a plate type fuel element of thickness 2a, its which is not possible to show in the diagram. Its cross section area we are taking as capital A, cross section which is perpendicular to this slide, and on both sides this element is covered by a cladding of thickness B. Now, generally in general reactors we will find that this dimension 2a is extremely small compared to the dimension in the other two directions, and hence it can be considered to be or can be viewed as a one dimensional problem. So, under steady state the heat transfer and the fuel can be written following the Cartesian coordinate system. It can be written like this. Just I repeat here, conduction is the only mechanism that is happening inside the fuel, this being a solid, and now the generalized heat conduction equation in 3D Cartesian coordinate can be written as these are the three diffusion terms in x, y and z direction respectively, plus the volumetric rate of heat generation is equal to the transient term. Now, here we are putting several assumptions. One, of course, one assumption is 1D, as I have already mentioned. So, in case of 1D, this one goes off and so is this one, and also we are doing under steady state. This is the term. So, this one also goes off, and limiting our analysis to a one dimensional problem. A few other assumptions also we have to consider, like one important assumption that we quite often consider is uniform rate of heat generation. Now, truly speaking, that is not true, and in the next lecture we shall be relaxing this assumption, but here as a simplified case, let us consider that the rate of fission heat generation is uniform throughout the entire reactor. We are also considering the properties to be constant, properties like this thermal conductivity of fuel and also for the cladding. That is why it has come out of the differential, and also we are neglecting any kind of volumetric expansion that may appear because of the change in temperature and any such kind of similar effects. So, we get the solution of this from x equal to 0 to a of this second order ODE. We need two boundary conditions to identify the value of these two coefficients. So, this can be one boundary condition where T naught refers to the center line temperature, and the moment we do not have too much information about the center line temperature. So, we are just putting a symbol T naught, and then dt dx at x equal to 0 is also equal to 0. Now, what does that mean? That means that the temperature profile is a mirror image on either side of the center line or with respect to the center line, and that is perfectly logical because the heat generation inside the fuel is uniform and its dimension in both positive and negative x directions are identical, and hence temperature distribution should also be identical on both sides, or I should say mirror image on either sides. So, dt dx at x equal to 0, if we use the condition, then we immediately have C1 equal to 0, and then putting the second condition we get C2 equal to T naught. So, this is the final expression for temperature profile inside the fuel. Therefore, temperature at the fuel cladding interface, that is I am talking about this particular surface. Here we need to put x equal to a there. So, if we put x equal to a, we are going to get the surface temperature as T naught minus q dot triple prime a square by 2 kf, and by rearranging this, the temperature change across the fuel center line to the cladding surface, that is T naught minus Ts, can be written as q dot triple prime a square by 2 kf, and if q dot represents the total power that has been produced by the fuel, that should be the volumetric energy generation multiplied by the volume of this, and this volume should be small a into capital A, because small a is the dimension of half of the reactor and capital A is a cross section area. Here one thing I should mention, the energy that has been produced in this half of this reactor, that gets transmitted into this side. Similarly, the energy that is getting produced in this side of the reactor, that is getting transmitted to this side, and therefore, we are only considering half volume while doing this energy balance or while defining this q dot. So, this q dot you can say as the energy produced or rate of power production of half of the reactor. So, putting this expression here, we get this final expression, and we can like what we do in common heat transfer, we can draw an electrical analogy to this and define a thermal resistance. Now, resistance can be defined as the driving force for the heat transfer, which is the temperature difference across the fuel divided by the heat transfer rate, that is delta T by q dot, and accordingly the thermal resistance for the fuel is A by 2 capital A into Kf. Now, we move to the cladding. There is no heat generation inside the cladding, and hence we have a very simple form of homogeneous second order ODE whose solution will be C3x plus C4 for x equal to a to b. Now, our boundary conditions can be at x equal to a T is equal to Ts, the surface temperature which we have evaluated in the previous slide, and at x equal to a plus b, that is at the outer surface of the cladding, it is equal to Tc. So, if we put both of them, this is the temperature profile that we are going to get. And now, we can apply the interface boundary condition. Interface boundary condition refers the rate of heat transfer, both the temperature and the temperature gradient or the rate of heat transfer should be identical at the interface of the fuel and the cladding. That means, at x equal to a, T or temperature should have a continuity, and the same condition we are using here. At x equal to a, T is equal to Ts for both cladding and fuel. And here we can use the second condition, that is the rate of heat transfer. Conduction is the only mode of heat transfer here, because both fuel and cladding are solids. So, minus k dt dx at x equal to a should be equal to the total amount of heat flask that is getting transmitted through that phase. Here we have used the Fourier's law of heat conduction, and the heat flux just that is coming out through one of the phases. Let me write it in a better way. The heat flux coming out of one of the phases should be equal to the energy produced in that half of the reactor, that is, as we have seen into previous slide, to a divided by the cross section area. That is why we are having this term here. Now, using this interface boundary condition, we can calculate, or we can derive get the derivative of this and put the condition x equal to a, and subsequently we get the temperature change across the cladding, that is Ts minus Tc should be of a form like this, q dot b by a into KCl. So, again drawing the thermal analogy, we can define a thermal resistance for the cladding as small a divided by a into KCl. Finally, the energy that has reached the cladding must go to the coolant stream, which is flowing on the surface of the cladding, along the surface of the cladding, and there the mode of heat transfer is convection. So, we can write a general energy balance between the cladding at the cladding surface, that is the amount of conduction heat received by the cladding should be equal to the amount of heat transfer to the coolant via convection under steady state, and hence the total rate of energy generation by half of the reactor should be equal to H into Tc minus T bulk. Here small h is the corresponding heat transfer coefficient, and accordingly we can define a film heat transfer, film temperature difference, delta T film, as the temperature difference between Tc and T bulk, and that is found to be q dot by Ah. So, we can define a thermal resistance for the film as 1 upon H, which is actually the very standard form of thermal resistance for convection in Cartesian coordinate. This is a typical temperature profile that we may have. Actually, in reactors you may find that the fuel and cladding are separated by small air gap or gap covered by some kind of inert gas. So, inside the fuel we are getting this kind of temperature profile, and this is the temperature change across the fuel, this is the temperature change across the cladding, and if the gap is there we are going to have a temperature change across this as well. And finally, this is the temperature change across the liquid film, this portion, the film of liquid which may get generated on the outer surface of this build, outer surface of of this cladding. So, we shall be doing that in the next lecture again, but as we have already calculated the 3 heat transfer resistances, so we can also combine them to get a combined expression of total temperature difference, that is the reason for having such a heat transfer, which is the difference between temperature at this particular point and the bulk temperature. So, T naught minus T bulk divided by heat transfer should be equal to the summation of all these resistances. We have already calculated the resistance corresponding to the fuel, the cladding, and the coolant or heat coolant film, I should say. And if there is a gap is involved, then we can also calculate the resistance for that gap and add to this. We can perform analysis of a cylindrical fuel element the same way. Here we have a cylindrical fuel pin of radius small a, and there is a cladding covering of the around the cylinder, which is having a thickness of small b. Here we can perform the similar analysis, but following the cylindrical coordinate system. So, this is the one dimensional steady state heat conduction equation in cylindrical coordinate system, and by solving this we are here, and then integrating it once more, we are getting in this particular temperature profile inside the cylinder, that is for r less equal to a. Now, we need to use the boundary conditions. Similar boundary conditions, at r equal to 0 the temperature is T naught, which is center line temperature, and again center line being a plane of symmetry, the temperature gradient will be 0 as well. So, putting the second condition, we can straightway say that C1 equal to 0. Like if we put r equal to 0 here and dt dr equal to 0 here, C1 has to be a 0. And then putting this other second boundary condition in the remaining expression, we get C2 equal to T naught, and accordingly this is the corresponding temperature profile. Therefore, temperature at the fuel cladding interface, where r equal to a if we need to put, we are getting the corresponding expression, and hence the temperature difference across the fuel is q dot triple prime by 4 kF a square. Rate of energy generation inside the rod can be given by like this, where pi a square h is the volume of this rod and q dot triple prime is the rate of energy generation per unit volume. So, if we use this definition in the previous expression, the temperature difference can be written like this. And now we can again draw the electrical energy to get the thermal resistance for the fuel, which actually will be this delta T divided by q dot. So, is equal to 1 by 4 pi h into kF, where h is the height of this cylinder that we are talking about. Again, neglecting heat generation inside the cladding, we are having this simplified expression, and then we can integrate this way. Now, the boundary condition can be to specify temperature on both sides of the cladding, that is T at r equal to a is equal to T s, and the second condition at the other edge of the cladding, that is r equal to a plus b, T is equal to T c. So, if we combine them, we get this particular expression. I would request you to derive this on your own. This looks complicated, but actually can be quite simple. And now again we apply the interface boundary condition, that is the total amount of energy that has been produced by the fuel that must pass through the cladding itself. So, K dou T dou H dou R at r equal to a into the area, corresponding area, should be equal to the amount of energy produced inside the cladding. Here 2 pi R h refers to the area of the cylindrical element at any radius r, and h is the height. And accordingly we get the temperature difference across the cladding is equal to q dot into log a plus b minus log a by 2 pi h kCl, and hence we can define the thermal resistance for the cladding as this, log of a plus b minus log a by 2 pi h into kCl. And finally, again we can define a thermal resistance corresponding to the convective heat transfer to the coolant by equating the energy transferred from the cladding to the energy received by the coolant. Small h again is the heat transfer coefficient, and hence we can define a film temperature difference as q dot by 2 pi a plus b into h into small h. So, the corresponding thermal resistance for the film is this. Hence, like in case of a planar element, for cylindrical element also we have identified the 3 thermal resistances, of course by assuming the properties to be constant, property like the Kf and Kcl. If we assume them to be constant, then we know how to calculate the 3 thermal resistances, and accordingly we can calculate either the bulk temperature if we have our knowledge about the center line temperature, or the center line temperature if we somehow identify all these 3, if we can calculate the or measure the bulk fluid temperature, which is not very difficult. One problem of course will be this small h, the convective heat transfer coefficient, which depends on the properties and also the velocity level of the coolant stream itself. But the 2 geometries that we have discussed here, both are quite simple. Like one important assumption was the uniform heat generation that we are having inside the fuel element, which practically is not true. Like in the previous module already we have seen that neutron flux can have quite complicated distribution over the reactor, and if the neutron flux is varying, then the heat generation has to vary in proportion. So, in the next lecture we shall be taking it from this point onwards, where this thermal resistance values will be utilized, but we shall be considering the neutron flux to be varying, and thereby we shall be able to do a more complicated and involved heat transfer analysis. So, I am leaving this up to today. Please go through the analysis and go through all these derivations. I would request you to derive on it all these steps on your own, and so that when you come for the next lecture, you know all the intermediate steps and you know how we are deriving every term this. So, thanks and bye for that.